Okay, slide your homework away, take your notes out please so that we can continue. Okay, get back in. Last time we were talking about a very important reaction in acid-base chemistry. The fact that two water molecules, just remembered some point I wanted to make, just real quick. Do we need an aqueous symbol here? We've agreed. Here? 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 Oh, forgot to write that in. When you have neutral molecules, you still need a state symbol, because they can be solid, liquid, gas, and an aqueous solution, right? We still need an aqueous symbol under neutral substances so that we know that they're dissolved in water. We're going to make the assumption that all the ions that we write in chemical formulas are in aqueous solution.
For these though, unless further stated, like, would it be aqueous then? Because like, any neutral things? So how would we know?
You'll have to be told.
Oh.
Sorry, back to where I was. I wanted to make sure I had got that point in. The two water molecules will compete with one another for their hydrogen ions and form hydronium ions and hydroxide ions to a small extent. That is to say, a few of these will form before we have equilibrium established. Yeah? Now, pure water has a very, very small amount of hydronium and hydroxides, and we end up with an equal amount of each, because for every water that gains a hydrogen ion and becomes a hydronium, we have a water that loses a hydrogen ion and becomes a hydroxide ion, right? So in pure water, we expect these concentrations to be equal, and they are each 1 times 10 to the negative 7 moles per liter. That is 0.000001 molar, right? A very small molarity. And of course, since pH is defined to be the negative of the logarithm of the hydronium ion concentration, if we know the hydronium ion concentration, we take the log, change the sign, right? I'll remind you that a logarithm, log of x, is the number you raise 10 to get x, right? So what number would you raise 10 to get 10 to the negative 7? Negative 7, right? So if we have numbers written in scientific notation, if the mantissa, the number out front here, is 1, then this is the same as 10 to the negative 7, and the logarithm of that number is just the exponent, isn't it? Right? So, what is the logarithm of that number? Negative 7, and we have to change the sign to get the pH, so the pH is 7. This is the point I made right at the end of the period. The pH of pure water is 7, not by coincidence. Not because someone had decided that their lucky number was 7, right? happens to be that this is the concentration of hydronium ions in pure water. And when we take the log and change the sign, we get 7. Okay? That's where that number came from. Now, we're going to jump ahead just a little bit, talk about something called Le Chatelier's principle. It's a French word, French name. Principle could be a French, originally a French word too, I think.
You guys know how to spell that?
It's real important to write it down. Now, Le Chatelier, it's not quite the right pronunciation because, if you were speaking French, you'd say Le Chatelier. You can't really say anything in French without the it's a hood. Not this. Le Chatelier's principle, here's what he came up with. We're going to talk about it briefly. We're going to use this basic idea because the idea is fairly simple. We'll come back and talk about it in more detail as far as why it's true and why it works the way it does a couple of chapters down the line. Okay? Just to give you an idea, there are lots of chemistry textbooks out there that do a chapter on equilibrium first before they talk about acid-base chemistry, because we use chemical equilibrium so much in talking about acid-base reactions. Okay? But this textbook does it a little differently. So here's what Le Chatelier's principle says, and here's why it works. We have two reactions that are undoing each other, don't we? These two are coming together and exchanging hydrogen ions to make hydroniums and hydroxides, but these two will also bump into one another and exchange the hydrogens right back again to make those things, right? And this reaction would be at equilibrium when the two are going at the same rates, right? Okay? Now, if I add more of these, how would I add more of these? Nope. And I'm using the word more. More water would have more of them. What I really should have said is, how can I increase the concentration of these? More water would not have a higher concentration. Okay? So how would I increase the concentration of hydronium ions in a bucket of water? Put an acid in. Preferably one of our stronger acids, right? Would be a better source of hydrogen ions to make more hydroniums. But here's the thing. If I add an acid to this solution, I'm increasing the number of hydronium ions. Well, if there's more of these, higher concentration, aren't these going to bump into one another more often? And that will speed up the backwards rate. Yeah? Which will reduce the amount of hydroxide ions. Now, we're going to talk about this in more detail and understanding of why these changes in concentration occurs are not important for the time being. But the effect is this. Hydroniums and hydroxides are on a seesaw. One goes up, the other goes down. Okay? Now, Le Chatelier's principle says this, and it's pretty elegant. Whatever you do to a reaction at equilibrium, the reaction tries to undo if it can. And I'm going to want you to write that down. You want to steal those? Sure. But not until... Oh yeah, you can leave me just 2 of each. That'll be fine. And not the brass. I don't need brass. Let me repeat it. Le Chatelier's principle, here's what it is. Whatever you do to a reaction at equilibrium, it will try to undo if it can. Whatever you do to a reaction at equilibrium, it will try to undo if it can.